Section 3.4 is about common functions, and we're going to talk about power functions and give an idea of how to graph them, spot them, and just to understand their general shape. Let's start with the definition. A power function is a function of the form f of x equals a times x to the n, where the constant a and the exponent n are any real number. So this isn't just a polynomial situation where our exponents are restricted to positive integers. Another important feature about this definition is that a power function, by definition, is a single term. So consider the four following expressions below. Pause the video and try to see if you can guess which are polynomials and which are power functions. The results are going to go as follows. The first one is a power function, but not a polynomial because I have a non-integer exponent. The second one is a polynomial, but not a power function because even though I have integer exponents, they're two separate terms. The third is both a power function and a polynomial because I have an integer exponent and only one term. And then the fourth is neither. It's not a polynomial because I have non-integer coefficients, and it's not a power term because I have two separate terms. And we emphasize this for the following reason. It's a very common mistake to think that every polynomial is a power function. Power functions and polynomials do overlap a little bit, but they still are their own distinct set of objects. Power functions can have any exponent, but only a single term. Polynomials can have several terms, but only non-negative integer exponents. Now we're going to talk about the graphs of some common power functions. Let's first consider power functions that have odd natural number exponents. The first are pretty easy. F of x equals x to the first is just going to be a linear function tilted at a 45-degree angle. G of x equals x cubed is going to have this S-shaped bend and pass through the origin. Then h of x equals to x to the fifth is going to have a similar S-shaped bend, but the difference is subtle. H of x is going to have a slightly tighter graph around the origin and around the x-axis, and it's also going to be steeper than g of x. Now the drawings of mine here may not do the differences too much justice, but if you put these into a graphing calculator, you can see that these will give similar but slightly different graphs. Basically, the larger an odd power on a power function goes, the more your graph is going to hug the x-axis, and the steeper your graph is going to get. Now we don't have a word for this S-shaped curve like we do for parabola, so we're just going to refer to it as an S-shape. We also want to talk about the infinite tails of this graph. This is normally called end behavior. Each one of these graphs has a similar trait. Towards the left, these graphs tend to negative infinity, and towards the right, they tend to positive infinity. In Chapter 5, we're going to talk quite a bit about end behavior, but really this just means I'm tracking these infinite tails on the graph. I want to see where they're going. And this is also a pretty hot topic in Calculus 1. Now we're going to look at the same kind of graphs, but with even powers. These are all going to give us parabolas. First we'll start off with the classic f of x equals x squared. Now let's let g of x be x to the fourth. We'll see that this parabola has a subtly different shape. It looks a little bit more saggy or flatter on the x-axis, and the curves tend to steepen a little bit. And this becomes more noticeable when we look at h of x equals x to the sixth. It kind of sags down a little bit more, it's a little bit more flat at the bottom in appearance, and the curves get a lot steeper towards the left and towards the right. Basically, the larger an even power gets, the flatter your graph will appear towards the origin, and the steeper your graph will get as you tend to the left or to the right. Looking at the end behavior, both the left and the right infinite tails of the graph all go to positive infinity. So ultimately, what's the whole point of doing all this? Essentially what we're aiming for is a better ability to get more efficient sketches of graphs, and we're viewing these power functions as building blocks. The next slide gives us kind of a basic example. I want to get a graph sketch for f of x equals to 3x squared and g of x equals to negative 2x cubed. This is kind of like what we talked about way back when we were graphing linear equations in two variables. We wanted something that was a little bit better than simply an x and y chart. And the mentality here is the following. I understand that power functions come with a basic shape, almost like a basic default shape that I can think about when trying to sketch the real graph. Now f of x and g of x here, they're not just power functions. I now have coefficients like 3 and negative 2 that will certainly affect our shape. So as the text on screen suggests, we're going to use some test values. I say to typically use values like -1, 0, and 1 because they're close to the origin, and computationally speaking, these are very easy to plug into functions and simplify quickly. So we're not making xy charts here. The idea is that for f of x, I know what x squared looks like. And once I plot a couple of points, I can connect the dots with that default parabolic shape and then get a pretty accurate sketch of our graph. So let's go ahead and plug these values into f of x. F evaluated at -1 gives me +3, f evaluated at 0 is going to give me 0, and f evaluated at 1 is going to give me +3 as well. So we can plot those. And since I know that this graph should look like a parabola, I'll connect the dots in that way. And from this we get a fairly accurate representation of what the function f of x equals 3 times x squared looks like. Now what I'm about to do is not a necessary part of the problem, it just kind of helps us see the difference here. I'm going to overlay this with what x squared by itself would look like. Essentially, x squared, or the default x squared power function, would be a slightly wider parabola. And this helps me kind of understand that this multiplication of 3 gave me a slightly thinner parabola. We're going to do the same thing for g of x. We'll plug in the same values, -1, 0, and 1, and plot the corresponding points. Now, if all I had were these 3 points and no other information, it might be tempting just to draw a straight line that connects them and say that we're done. But that wouldn't be accurate here. I know that g of x comes from the power function x cubed, which has an S shape. So as I connect these 3 dots, I have to do so by observing that shape. So performing that action will give me the following graph. And just like before, I'll draw the regular default x cubed graph on top of it just so we can see how they differ from each other. Now it looks like -2x cubed, g of x itself, is just a little bit thinner than the original power function x cubed, but the biggest difference is that it looks mirrored. They look a little bit mirrored from each other, and that's what that multiplication of -2 is actually doing for us. What we're essentially observing here is that when we take a power function and multiply it by a constant, we end up with a transformed version of the default graph that we saw on the last slides. That's why it's healthy to think about power functions as building blocks, because I can use them to envision bigger functions by transformations like this. For our next set of functions, we're going to look at functions who have the form of x to the -n for a natural number n. We understand that with negative exponents, that's the same as bringing something down to the denominator. So f of x equals to x to the -1 is the same thing as f of x equals to 1 divided by x. And that's what functions in this slide are going to care about. Functions that look like 1 divided by x to the n, where n is a natural number. Let's also look at the infinite tails of this graph. We notice that as the graph approaches the y-axis, it goes to negative infinity from the left and positive infinity from the right. However, the infinite tails that stretch infinitely to the left and to the right, it looks like our graph is actually tending to the value of 0. Again, this is the topic known as limits that you see a lot in Calculus 1. Now that we've seen f of x equals 1 over x, let's look at g of x equals 1 over x squared. Here we see a fairly similar graph, but because I'm squaring values, everything flips above the x-axis and becomes positive. So in this case, it looks like as the graph approaches the y-axis from both sides, it goes to positive infinity. But as my x values get infinitely large, my graph is tending to 0. Next, we've got h of x equals 1 divided by x cubed. This graph is going to look very, very similar to 1 over x, but the idea is that as my graph is getting a little bit closer to the y-axis, it gets a little bit steeper and it hugs the x-axis a little bit more. So the difference is subtle, and it's a little bit hard to see, especially with the way I might be drawing it, but the h of x graph does have a graph that hugs the x-axis a little bit more and gets steeper as it approaches the y-axis. Last, we'll look at the graph of k of x equals 1 over x to the 4th. Kind of similar to our parabola functions, this graph seems to sag down a little bit more, kind of hugging the x-axis a little bit more tightly. It's a little bit further away from the y-axis, and it looks like it's getting steeper as it approaches the y-axis. Alright, thank you for your attention, and join us on our next video about piecewise functions.